Everyone. So in this video, I'm going to talk about negotiation and bargaining. And you see my old date here is because almost exclusively during ordinary semesters, I don't really teach a whole lot from the slide I do. This is like one lecture. It's pretty much always on the dry erase board. So I'll go over some of that stuff. And unfortunately, this is like one of the things that's just heartbreaking is this is one of my favorite lectures to do because we teach it with an example. We do an experiment. And so typically we have $12 or $15, and I'll have stacks of $12 or $15 and then get partners or volunteers to come down and engage in exactly the bargaining activity that we're talking about. As you might imagine, it's super lively, it's a lot of fun, and it's a really good way to learn the concept. And we can't do that now, and so I have to go back to these slides. So, all right, fine. What I'm going to do here is I'm going to talk about the basic models, some basic economic models of bargaining, and think about what intuition we can gain from this. One of the reasons why this is super important is think about when we're talking about Porter's five forces for our entrepreneur. One of the important threats to profitability is the threat from suppliers, and there's scope for negotiation between suppliers and also between like large buyers. And so that's kind of the place where this is really relevant. In particular, like if you had an online like internet retailing business, one of your major costs would be shipping. And so you'd be doing kind of a lot of negotiation and bargaining between yourself and like UPS or yourself and FedEx or some of these other companies. And so anyway, so the point is like this is really useful for that. All right, so the simple example, suppose we have Sandy and Mike negotiating over how to split a bowl of ice cream. The longer the negotiation takes, the more ice cream melts. Suppose they're making alternate offers. Sandy makes the first offer, Mike can accept or reject. If Mike rejects, Mike makes a counter offer, Sandy accepts or rejects. If Sandy rejects, Sandy makes another offer, Mike accepts or rejects until all the ice cream melts. All right, so the idea is we've got this pie, this bowl of ice cream. We're trying to bargain over it, and there's this problem where the longer it's taking us to bargain or to come to agreement, the smaller the pie is getting, right? So there's this sort of time pressure. So situation A, suppose it's very hot out. If Mike doesn't agree to Sandy's first offer, the ice cream will melt completely before Mike gets a chance to make a counteroffer. This is a single round game. What happens? Well, in this situation, there's a massive first mover advantage for Sandy. And so let me see. To be able to make, I'm going to skip back to my slides skip back to this portion to explain what's going to happen. Actually, let me finish this up for those in the video. So this is a single round game. This is like an ultimatum game. You have a take it or leave it offer. And what ends up happening is like if you don't come to an agreement, you both lose. And so what ends up happening is we expect Mike should agree immediately. And then Sandy is just going to be able to guarantee whatever term Sandy wants. So there's a massive first mover advantage for Sandy. All right, let me skip back to this, and that's fine. I'll just do this. Good radio, Ben. Good radio. All right, so it's a little less hot now, situation B. If Sandy's first offer is rejected, we're assuming the ice cream's going to melt to 2/3. If Mike's counteroffer is rejected, we assume the ice cream's going to melt down to 1/3. And then if the second offer is rejected, the ice cream's gone. The rounds for this game, Sandy's offer, Mike's accept or reject. Mike's counteroffer, Sandy's accept or reject. Sandy's second offer, Mike's accept or reject. And then ultimately the end of the game. And so, I don't know. I'm going to have to go over these. This is driving me absolutely crazy. So I'm not enjoying this very much. All right, so this is typically the background that I would put on the board and kind of talk about some stuff like this, kind of bringing us into this lecture. And this is going to pick up the slides kind of where I left off, and then I'm going to go back to the slides. So first off, I pose the question of like, what's a fair allocation? Is it 50-50? Sometimes our intuitions tell us that it is, but maybe it's not, right? So Varian, so think of like the intermediate micro class, Varian says an allocation is fair if there's no envy. So maybe it's the case that 50-50 split is fair, but maybe it's not. It's really difficult. So suppose you're bargaining over 2 chocolate cookies. One's vanilla and the other's chocolate. Suppose Jack loves chocolate and Emily is allergic to chocolate. Then Giving 2 chocolate cookies to Jack and 1 vanilla cookie to Emily is not a 50-50 split, but there's no envy. Therefore, it's fair according to Varian, because Emily can't have those cookies anyway, and Jack has more cookies. So, all right. What about the case of alternating offers, such as what I've just described? So, suppose we have Ann and Bob bargaining over 12 ounces of ice cream, and it's melting. Suppose we have one period. This is t equals 1. Initially, Ann's going to make an offer. Bob can accept or reject. So if Bob accepts, they're going to split according to whatever was Ann's offer. If Bob rejects, they're both going to get 0. So this is an ultimatum game. An ultimatum game, typically think of like some laboratory experiments in economics. First, there's the dictator game. You have subjects with like $10 and they can choose how much money to give to some random other player. So a lot of people will end up keeping all $10 themselves. A lot of people will make the 50-50 split. Then we could think about, well, what about the ultimatum game where the recipient has some recourse? They're going to look at the offer. They're going to either accept or reject. If they reject, nobody gets anything. If they accept, then the split goes accordingly. So this would be the situation in the laboratory where you'd have $10. You decide how much to offer to the other person, and you'd want to offer enough so they accept. Well, in standard economic theory, our story is you should be able to accept any small positive amount, because in the ultimatum game, getting a penny is better than getting nothing. And so the smallest possible offer is going to be accepted. In practice, it turns out in the ultimatum game, a lot of research shows that proposers will offer somewhere in the range of like a 70-30 or an 80-20 split, and respondents tend to reject anything less generous than about a 70-30 split. Like if I'm getting $3, if I'm getting less than $3, that tends to typically be the threshold point between where the recipient from the ultimatum game will tend to start rejecting. There's also a lot of 50-50 splits and so on and so forth. But the basic idea back to this game is the subgame perfect Nash equilibrium is Ann is going to give Bob the smallest amount such that Bob accepts for sure. So Ann's going to give Bob just enough to make Bob want to accept. In our example here, Ann actually doesn't have to give Bob anything, because Bob's going to be indifferent between getting 0 from being offered 0 and 0 from rejecting Ann's offer. We're assuming Bob doesn't have any type of pro-social, social norm, psychological emotions. Like, we're not doing psychological game theory. There's an interesting realm of behavioral economics that can say some other stuff here. We're just assuming standard economic preferences. All right. In the 2-period game, suppose now we've got 12 ounces of ice cream. It's going to shrink to 6 ounces by period 2. Ann makes an offer. Bob can accept or reject. If Ann's offer is accepted, they're going to split accordingly. If Ann's offer is rejected, Bob gets to make a counteroffer. Then in period 2, Bob makes the offer. Ann accepts or rejects. If Ann accepts, the ice cream is split accordingly. If they reject, or if Ann rejects, they both get 0. So we'll use backward induction to solve this, determine what's going to happen. In the last period, Bob's going to offer 0-6. Bob's going to offer Ann nothing, and Bob's self 6. Ann is actually indifferent and will accept, because 0 from being offered 0 is the same as 0 from rejecting. In the first period now, Ann is going to look forward, and Ann is going to realize Bob is going to get 6 for sure in the second period, and Ann is going to get 0. So Ann has to offer Bob at least 6, right? If Ann offers Bob at least 6 in period 1, Bob's going to look forward and say, oh, I'm going to get 6 in period 2 anyway. I might as well accept 6 now. So that gives us the 50-50 split, right? So Ann offers 6 and 6, which is just enough to keep Bob indifferent, and Bob will accept. So the subgame perfect Nash equilibrium in this case is an equal division, 6 and 6. What about 3 periods? So now we've got 12 ounces. That becomes 8 ounces, becomes 4 ounces. And I wish this is like $12 becomes $8 becomes $4. It's a lot more fun. Or 15 becomes 10 becomes 5. Anyway, so Ann offers, Bob accepts or rejects. Bob offers, Ann accepts or rejects. Ann offers, Bob accepts or rejects is the structure. All right, well, the ice cream's melting. So what's going to happen? By backward induction, we go to the end of the game, Go to the very end, and we're going to say, okay, in period 3, Ann is making an offer. Now there's only 4 ounces. Ann's going to offer 4-0, meaning Ann keeps 4, Bob gets 0. Bob will accept because 0 from this offer is the same as 0 from not accepting. In period 2, Bob's going to look forward and realize Ann is going to get at least 4, right? Ann is going to get 4 in period 3 because Bob's going to accept the offer where Bob gets 0. So in period 2, Bob realizes Bob has to offer Ann at least 4 out of these 8 ounces. Okay, so Bob is going to offer 4-4 to keep Ann indifferent. In period 1, Ann is going to look forward, realize that Ann is going to have to offer Bob at least 5 to keep Bob indifferent, or at least 4 to keep Bob indifferent. Because in period 2, Bob is going to get 4 because Bob only has to offer Ann 4 because Ann would get 4 here. So Ann's going to get 4 as a result of the period 3 offer if we make it to period 3. So Bob's going to offer Ann 4 in period 2. So Bob offers Bob's self 4, which means Ann is going to have to offer Bob 4 in period 1 so that Bob realizes I might as well accept in period 1 than let this game persist. So Ann is going to offer Bob 4, keep 8 for Ann's self. So Bob is going to get at least 4. Ann is going to offer 8-4, 8 to Ann, 4 to Bob, and Bob is going to accept. This subgame perfect Nash equilibrium is our 2/3, 1/3 split, right? 2/3 of 12 is 8, 1/3 of 12 is 4. All right, so this brings us to Rubinstein, thinking from 1982, thinking about the T-period bargaining game. This is the economic theory behind this. A couple principles. First off, bargaining should never go beyond the first round. The settlement should be immediate, right? Bob's not going to wait around. Ann's not going to wait around. They're going to agree immediately to this 8-4 offer in the game we just did. Also, if we have an even number of periods, the subgame perfect Nash equilibrium is the 50-50 split, one half, one half. So if we had 2 periods, the $12 or ice cream got split to 6 and 6. Here we have an odd number of periods. What happens? Well, it's this formula: t plus 1 divided by 2t for the first mover, and 1 minus t plus 1 divided by 2t for the second mover. We had 3 periods. 3 plus 1 is 4, divided by 2 times 3 is 6. 4 divided by 6 is 2/3, and then 1 minus 2/3 is 1/3. That's exactly what happened in our 3-period game. Think about what happens as t gets really big, as we get a large number of periods. This is actually going to tend towards the 50-50 split. So where would we get a large number of periods? So suppose there's no deadline, so you can go back and forth and negotiate for a long time, and there's maybe a gradual decay. So the pie's not splitting or not shrinking. Ultimately, bargaining can yield the equal split with sufficient time to negotiate. That's sort of an important principle. Some other things here from Rubinstein. So when offers and demands are made sequentially in bargaining games, and if a speedy resolution is preferred to one that takes longer, there's only one offer that a rational bargainer will make at the outset of negotiations. And the rational bargainer's opponent, if rational also, has no rational alternative but to accept immediately. So there's a problem. There's the worry, so they have to balance off the worry about making an offer that's not refused because you want to avoid the pie shrinking, and you have to balance off the worry about making offers that's unnecessarily generous. So you don't want to be too generous, but you don't want to be insufficiently generous, because if you're too generous, then they're not going to accept, and then you're going to lose surplus. And if you make the offer that's too generous, then they will accept, but you've given away too much. Interestingly, so Binmore, Rubinstein, and Walensky, 1986, showed that this is actually equivalent to the Nash bargaining solution. So think of like John Nash. John Nash's Nobel Prize shared the Nobel Prize with John Hersani and Reinhard Selten for kind of contributions around the Nash equilibrium. That's kind of what John Nash is known for, but maybe so a really important contribution was in bargaining, in cooperative game theory here as well. And so anyway, so going back to situation A and situation B, if it's hot out, Mike doesn't agree to Sandy's first offer, the ice cream completely melts before Mike gets a chance to make a counteroffer. This was like the one-shot game. This is where Sandy has a huge first mover advantage. If the pie shrinks more slowly, this is like my 12-ounce, 8-ounce, 4-ounce game. Now we have a situation where we have this outcome where if we were to get to the third round, yeah, Sandy would offer, in my example, was like 4, and then Mike would get 0. Mike accepts. Knowing this, what does Mike offer in the first round? Would Sandy accept? Knowing this, would Sandy offer in the first round? Will Mike accept? We actually walk through all this. What's the equilibrium of the game? It's the 2/3 to the first mover, 1/3 to the second mover. Sandy's first mover advantage went down substantially in the odd game. Oh, one question you might have is like, what's this epsilon doing? This is saying Sandy would offer 1/3 minus just a little bit, and then Mike would get just a little bit. Epsilon is some small positive number. If you want to do your bargaining situation, this is kind of like the second degree price discrimination where I said you'd want to, so in the second degree price discrimination in the advanced pricing lecture, I had the example where you're pricing the high product at 90 or 89 instead of at 100. That 90 or 89, we could have also written this as like 90 minus epsilon. The idea is like it's just enough to make them strictly prefer, right? So the worry would be, suppose you don't like my logic that Anne or Bob or Sandy or Mike is going to be indifferent between 0 from rejecting and 0 from accepting an offer that involves 0 to them. We could give them the small positive amount. We could give them epsilon that'll make them strictly prefer like 1 penny to nothing. All right. So suppose we extend the game even longer. The ice cream maybe takes longer to melt, or analogously, the counteroffers can be made quicker. The first mover advantage decreases. This is our story about if you increase the number of rounds of the game, well, to 101 rounds, Sandy ends up with like 51 over 101. Mike ends up with 50 over 101 plus epsilon. Now we've got something a lot closer to the 50-50 split. All right, what do we learn from this? Well, the melting ice cream can be thought of as like the continued cost of negotiation. Lawyers' fees, time cost, the cost of a strike, whatever is the case. There's a first mover advantage, but this advantage disappears as the game persists or as the speed of counteroffers increases. If you're the first mover or the current mover in the game, you become the current first mover. In more general negotiation games with imperfect information, there can be a benefit to strategic delay. So suppose it's your turn to make an offer. What you'd like to do is make the offer and then allow your opponent to accept or reject, but commit to a time delay before being able to respond. The longer is the delay, the more the ice cream melts, the more before they get a chance to respond, and the more likely it is that they accept whatever is the current offer. So that kind of goes in your favor. Tricky issue is how you allow them to respond yes or no to your offer, but don't allow them to counteroffer until after the delay. So you could send an intermediary with limited power, so send a lawyer to the negotiating table who has the authority to enact your current offer if they accept, but not to accept a counter proposal. And there's a lot of other type of commitment devices. If you invoke conversations with your partner or whatever is the case, these are different ways that we can implement some type of strategic delay if you'd like to buy yourself some time. Note the delay needs to be credible, otherwise, because the idea is that it's the threat of the delay that causes the earlier agreement. And so if it's not credible, then once you're faced with the decision of whether you want to delay, if it's an incredible threat, if it's not in your interest to delay, you actually wouldn't. So then that loses that strategic power. Here's a more general situation. Think about a purchasing setup. Maybe this is between yourself and then suppliers. So a notation that I'll use is RB, that's the reservation value of the buyer. This is the price at which the buyer gets no surplus from the deal, no economic surplus, no value added. This depends on the buyer's outside options, right? This is my reservation price. This is the highest price as a buyer that I would pay. RS is the reservation value of the seller. This is the price at which the seller gets no surplus from the deal. And it depends on the seller's outside alternatives. Obviously, RS must be less than RB for a deal to take place. Buyers must have a higher valuation than sellers' costs for there to be gains to trade. Now, if the deal is completed at the beginning of the game, in period 1, the buyer is going to end up getting, well, whatever is their valuation minus the price, and the seller ends up getting whatever is the price minus their cost, essentially. This is just like consumer surplus and producer surplus, right? Willingness to pay minus price is consumer surplus, price minus cost is producer surplus. That's essentially what this is doing. Buyer surplus, seller surplus. All right, but what if we don't agree in the first period? We want to allow these surpluses to go down if the deal takes a long time. Maybe there's lawyer fees, there's melting, we need to get the product to the market quickly and we're losing profits, So suppose the deal gets finalized in round T. the buyer is going to get a discounted surplus, right? This is a discount factor, delta. So we've got delta somewhere between 0 and 1, where if delta is really big, there's very little discounting. But if delta is really small, there's a lot of discounting, such that if we're far enough in the future, there's no surplus because we wasted it. Same thing for the seller. The seller gets some surplus. We're going to multiply whatever is its producer surplus by some number between 0 and 1 that reinforces the idea of like what is the future value of that surplus. All right, so the idea is we want to think of delta B and delta S as patience parameters. It measures how patient the buyer and seller are. The higher delta means more patient because that means that your surplus persists as close as possible in its entirety into the future. The lower delta means less patient because your surplus evaporates into the future. So if we first assume perfect information, each side knows both their and their opponent's own deltas and R's. If they have the same patience values, delta B is equal to delta S, both have the same degree of patience, then the equilibrium approaches the midpoint between the offers. So you could say this: as the speed of the offers gets quicker, as the players get very patient, we end up getting the price is equal to, well, look at this. This is going to be RS plus 1/2 RB minus RS is the middle value, right? If I take the difference between RB and RS, RB minus RS, that's just the total economic surplus. This is the difference between willingness to pay and willingness to accept. Multiply that by 1/2 gives us the midpoint. Add that to RS, that gives us, RS is going to be the lower bound that gets us to the middle. Equivalently, I could have written this as like, RB minus this stuff. All right, fine. The point is we're trying to find a point halfway between the reservation values, and that's what we're expecting if we're equally patient. Now, there's a bit of a first mover advantage when both players are impatient. It disappears for higher patient levels or as the speed of offers increases. And then what happens if the patient levels differ? What happens if we're differently patient? Well, it's really complicated, and so we won't go with it. It's even beyond like a Econ 401. It's even beyond like an intermediate micro question. But as the saying goes, patience is a virtue. So if it's the case that the buyer is less patient than the seller, we're expecting for a higher price, right? A price above the midpoint. If the buyer is more patient than the seller, we're expecting for a lower price below the midpoint. According to like whoever is more patient is going to pull the price in their direction. The buyer wants low prices, seller wants high prices. The size of the difference between delta B and delta S matters. The more impatient you are, the worse you do, because the more that you're willing to give up to your opponent immediately rather than sacrifice due to the time passing in the future. As a buyer, you are likely to get a better or a lower price. The lower is your reservation price. The lower is the reservation price of seller. These are all things that will tend us towards lower prices. The higher is your patience. The lower is the seller's patience. As a seller, you're better in the reverse situation. The seller wants higher reservation prices, wants lower patience for buyer, higher patience for the seller. Can you change these factors? Well, you could look for substitute buyers or sellers, and you definitely don't want to take actions that make you locked into your opponent. You don't want to be specific to that opponent. So you want to do things that keep your reservation price low if you're a buyer, keep your reservation price high if you're a seller, so that you've got good outside options. Do take actions that lock in your opponent to you. Make your opponent's reservation price low if you're a buyer. Make your opponent's reservation price high if you're a seller. And then ultimately, the choice of when negotiations occur can also affect patience levels too, especially timing really matters. Notice that in the perfect information game, where everyone knows everything, the agreement is always reached in the first round, as we showed earlier here. It's kind of like the specific case. Also, it's probably unrealistic to expect that we know everything, that we know your reservation price for both, and we know everybody's patience parameters. When there's imperfect information about reservation prices and patience, there's more room for strategy, such as if you're a buyer and if you want to convince your seller that if you're a buyer, you want to convince the seller that you have a low reservation price and a high patience, even if you really don't. So you might make statements about your reservation price and about your patience parameter. This is like the proverbial negotiation for a car where you threaten to walk away from the deal, right? So taking actions that signal your reservation price is low or your patience is high. Maybe take a really long time to make counteroffers that signals high patience. Walk away from a deal that signals low reservation price. There's strikes and so on and so forth. Ultimately, actions more credible than statements, but statements can also work, especially because what really matters is beliefs. You can, in that same vein, you can often manipulate the perceptions of your opponent's patience and reservation price. So you might try to convince the seller that you know or believe you know or are going to behave as if you believe they're impatient or have a low reservation price. And this is going to affect how they believe that you're going to respond in negotiations to them, and that can be important. Ultimately, do your due diligence, do your research. Some facts might suggest the seller has a high patience and a high reservation price. Ignore those while negotiating. Other facts might suggest the opposite and bring those up during negotiation. Notice, though, of course, in any strategic situation, you as well as your opponents might be following the same advice, following the same strategy. So suppose you have multiple issues you're negotiating on. Many times, two parties are negotiating over more than just price. So maybe you're negotiating with a contractor over the price and the time until the project is completed. You might prefer the lower price and the lower time. They prefer the reverse. So what happens? Well, here's an example. Suppose your utility or profits from a deal, price and then time, is going to be your utility function over price and time. The seller, the contractor's utility over or their profits over price and time is V of P of T. Yours is U of P of T. Let's think about how to maximize total utility, total surplus between these traders. So total utility, TU of P of T, is equal to U of P of T plus V of P of T. To maximize total utility, you're going to choose price and time to maximize. We get two first order conditions. du dp equals minus dv dp, and du dt is equal to minus dv dt. So du dp equals minus dv dp, du dt is equal to minus dv dt. So derivatives with respect to price we have my utility with respect to price and their utility with respect to price, and then the derivative of my utility with respect to time and their derivative of their utility with respect to time. If you divide through the first order conditions, divide them by each other, right? So divide these across, we end up with du dp divided by du dt equals dv dp divided by dv dt, right? This is like marginal utility of P divided by marginal utility of T equals marginal utility of P divided by marginal utility of T to our two traders. What are these quantities? This is like a marginal rate of substitution, right? This is like my MRS. My MRS trading off, my marginal rate of substitution trading off price for time, and their marginal rate of substitution trading off price for time. So the marginal rates of substitution should be equalized to maximize overall benefits. And then you can think of the economic intuition. If I can gain more by giving up some time to save money or vice versa, we should do that. What's the point? With multiple issue negotiations, you can often find mutually beneficial changes, small adjustments to the proposal, making both the buyer and the seller better off. And then, for obvious reasons, then these possible trade-offs and the others that result should be investigated to be able to do this optimally. All right, the summary. The other things we want to say here, there's a power of patience and your outside alternatives. Definitely don't volunteer your own weaknesses. Definitely play up your opponent's weaknesses. Definitely do volunteer your own strengths and ignore your opponent's strengths, at least as regards actually negotiating. Think about how your current actions affect future bargaining power, because especially if you have a repeated interaction with the same vendor. And then think about the context of this long or short. Do you have a long or short-term relationship with this opponent? And then what's the value for the future? So, all right, I hope you enjoyed this video. I'm going to go ahead and conclude here.